Welcome back to the class Artificial Neural Networks and Deep Learning. This part is about simple regularization methods that will allow us to address the problem of overfitting. For all regularization methods, we always split the database into two parts. We put one part of the data in the so-called training base that is used to optimize the parameters, and put the other part into the validation base that's sort of used to mimic future data. The two data sets are used in a slightly different way. The training set is used as before to minimize an error function. Here's the quadratic error function, it could be some other error function, and we minimize this by changing the parameters using gradient descent. At the same time, we look at the performance on the validation error, on the validation set. So the validation set sort of plays the role of future data. To illustrate how this works, let us return for a moment to the problem of regression. Each input data point is in the database connected with a target value. The target itself is a noisy version of this green sinusoidal function, and we approximate this after optimization with this red function, which is our prediction. So this is one data point, this is a new data point, and we would predict the red value. Now let's do this, and we change the flexibility of the network by changing the number of parameters. We have seen this in an earlier video. So with 4 parameters, we already get a pretty good performance. With 9 parameters, it might be slightly better. And with 10, it's perfect on the training data. But suddenly the performance on new data is much worse. So we can use the number of parameters to control the flexibility of the network. The more parameters we have, the more flexible the network is, the lower the training error gets. But if we increase the flexibility of the network, then the generalization error as measured on the validation data increases. So the best flexibility is the location where the validation error is minimal. This is true for regression problems, but this is also true for classification problems. Deep multimodal networks are flexible and can be trained by backprop to minimize the classification error, but we have to avoid overfitting, and we can address the problem of overfitting by splitting the database into a training base and a validation base. How would that work in practice? Here's a pseudo algorithm, a very simple approach. We play with the flexibility, which means for us at the moment, we play with the number of hidden neurons and the number of layers in the network. The more hidden neurons, the more layers we have, the more flexible the network becomes. Then we split the database into training base and validation base. Then we optimize the parameters. Since the algorithm may get stuck in a local minimum, we do this several times with different weight initializations. We iterate until convergence, which means we do gradient descent on the training data. Then we measure at the end, we measure the validation error. Then we report the mean training and validation error and the standard deviation to know how safe we are. And finally, plot the two against each other, and we pick the optimal number of layers and the optimal number of hidden neurons by looking at the configuration which gives the smallest validation error. So far we have played with the number of neurons in the network. This is a rather costly method. There's an alternative which is called a regularization method with a penalty term that amounts to modifying the loss function. Let me explain what this means. We said the flexibility is the number of free parameters. In the past, in the previous part, we said flexibility means we have to changing flexibility means we have to change the number of neurons or the number of layers. However, we can do it differently. Instead of changing the number of free parameters, we keep the actual network structure, the actual number of free parameters the same, but we introduce something like an effective number of parameters. And this is how it works. We use on the training set a modified error function. This is our normal part, and this is the extra part, which assigns a cost, a penalty, an error to very, very flexible solutions. So now we train on the training set with this modified loss function. I put a tilde here to indicate a modification. But occasionally, but after conversions, we check the standard error function on our validation set. So a specific example would be the weight decay, which is also called L2 regularization. We take all the weights, not the thresholds, but we take the weights, all the weight parameters, we square them, and then we have this parameter lambda that controls the flexibility of the network. If lambda is 0, the network is very flexible, assuming that we have many hidden neurons, many hidden layers. And then if we make lambda bigger and bigger, it becomes more costly for the network to use big weights. And the idea is a little bit that big weights are needed to implement very flexible separations between positive examples and negative examples. If you have very small weights, then essentially the network is very close to a linear function. Increasing the network weights puts therefore a constraint that shifts the network more to a linear implementation. So this is the modified error that we use on the training set, and then we check after conversions the normal error on the validation set. So if you use here a quadratic error function, then we use here again a quadratic error function. If you use here different error, then we would also use a different error here. Note that the validation error is not measured with this extra penalty term. This penalty term, because it's squared, is also called a L2 regularizer. If you just put the absolute values and no power, then it would be a L1 regularizer. The logic is the same. Big weights need to be penalized because big weights are needed to implement very flexible solutions. So a little quiz to check what we have seen so far and apply it. We increase the penalty parameter lambda. Increasing lambda means the flexibility of the fitting procedure decreases. Yes or no? Yes, this is correct. Increasing lambda, the effective number of free parameters decreases. Yes or no? Yes, this is correct. Effective number is exactly what I mean by controlling the flexibility. Then the third claim, increasing the penalty parameter lambda, the explicit number of parameters remains the same. Yes or no? And yes, of course, that's the whole idea. You keep always the same network structure, but you play with lambda. So if we increase lambda, the flexibility decreases. Let's now apply this. Let's look at the specific example with the sinusoidal function, noisy version of it, noisy data points, 10 data points, 10 parameters. So we have a very flexible network, but now we control the flexibility with a weight decay penalty term, a L2 loss regularizer with parameter lambda. Decreasing lambda means increasing flexibility. So what we plot here is the validation error. This is this function here, and we also plot this error, which means just this part, on the training, and we see that this goes down. So if I have a very flexible network, I see overfitting. If I increase lambda a little bit, I will find a minimum somewhere over here, and this would then be the best choice of lambda. So again here, the error as a function of flexibility, and the idea is now that we do not change flexibility in terms of changing the number of hidden neurons, but we just control flexibility via our penalty parameter lambda. So this would be decreasing lambda. So let us summarize what we have seen so far. Using these simple regularization methods with a penalty term, we can keep the real number of parameters fixed and large and still change the flexibility via changing lambda. And this is a standard method in all fields of machine learning, not specific to neural networks. In the context of neural networks, this means the following. We can always work with a fixed large number of hidden neurons. We can take a very, very deep network structure, and then we are going to control the flexibility via regularization methods. And this is how it would be implemented. We change the flexibility, which now means we choose lambda. We split the database into training set and validation set. We optimize the parameters, iterate until convergence on this modified training error. Then we report the standard error and on the training base and on the validation set. We report the two, we plot the two against each other, and then we pick the optimal lambda, which means the one where the validation error is lowest. So this is the method controlling flexibility by regularization. Note that weights are parameters, but lambda is now also a parameter. It's sometimes called a hyperparameter. Now this might be a bit weird because we want to control the number of parameters, but we add an extra parameter. So it could be, if we have many penalty parameters, that we make the network flexible again in the sense that we can do overfitting again. So we optimize lambda by looking at the validation set. So the validation set is no longer future data because we have used it to optimize lambda. In most cases, this nevertheless works. However, if you have enough data and if you have many hyperparameters, then it's better to use a double split and keep some data aside to really mimic future data. And this is what we are going to look at in the next part.